Right. This one, we want to look at this graph here, right? And we're going to calculate percentage purity. Now, if you have a graph like this that starts from 0 and then the amount increases, and then the amount starts increasing, right? So we are saying that from 0, then the amount is increasing, then the amount is stationary. This is what you should be reminded of. A product starts from 0, right? From the beginning of the reactant, of the reaction, the product starts from 0. So you look at from here up to there. This section here, we say the reaction is faster, and we say then from here up to there, the reaction is slow, and then at this stage here, the reaction has stopped. Between 20 and 30, the reaction has stopped. Then we said between 0 and 10, the reaction is faster. And from 10, and then between 10 and 20, this part here, the reaction is slow. The reaction is slow here. The reaction has stopped here, and the reaction is fast here. So it is fast, slow, stop. Then the rate of reaction is increasing here between 0 and 10. And then we say between 10 and 20, the rate of reaction is decreasing because now it is slow. Then between 20 and 30, the rate of reaction, we say it is 0, the rate of reaction. Right, just for grade 12, rate of reactions. We're just reminding you. Okay, fine. Now, where the graph is flat, we say the reaction has stopped, meaning that this reaction has taken 20 seconds to come to a complete stop, because it starts being flat from 20 seconds going forward. So it has stopped. It takes 20 seconds to stop. But anyway, that is for rate of reaction in grade 12. But let's look at the calculation. The calculation part is for both grade 11 and grade 12. Okay, so let's check. Now, we are saying after the reaction has stopped, the amount of carbon dioxide is 200. So a volume that is produced here is 200 cubic centimeters, right? And then they gave us, when we read the graph, they say 4 grams of impure calcium carbonate is reacted with sulfuric acid, right? But when we look at the information, we know that for carbon dioxide, we're given 200 cubic centimeters that is produced. And it is, right? So they say write down the volume in cubic centimeters of carbon dioxide that is produced at the end of reaction. We know that here at this stage, the reaction has ended, and it ended while the volume, when it ends, the volume of carbon dioxide is 200 when it ends. So the answer to number 1 is 200 cubic centimeters. That is the volume that is produced at the end of the reaction, right? So now let's look at number 2. It says calculate the number of carbon dioxide molecules produced at STP, right? So first of all, let's check what is it that we are going to do, right? We are given the volume of carbon dioxide, which I must convert to, it's given in cubic centimeters. I must divide it by 1,000 so that it becomes decimeters. So in decimeters, it is 0.2. It is 0.2 cubic decimeters. Now this volume of carbon dioxide, okay, it is a volume at STP. At STP. This volume is a volume at STP. Right. Now, it means now I'm going to use the formula that says N is equals to V over Vm because of the weight STP. All right. Remember we said when you look at your formula sheet, you should write this statement to remind yourself. Particles must concentrate at STP. It means when they mention the word STP, this is the formula that deals with STP. When they mention particles, particles can be molecules, atoms, ions, or formula units. When they mention that, then the formula is this one. Then, right? So we are going to use these two formulas. First of all, I'm going to get number of moles using this formula. Okay? Then after getting number of moles, I use those number of moles in this formula to get the number of particles or the number of molecules of carbon dioxide. Right. So I use this number of moles. I calculate number of moles first, then use those number of moles where here to get the number of particles there. Right. So from the volume that is given to us, I'm going to use this volume to calculate the number of moles of carbon dioxide. Okay, so we are given volume of carbon dioxide. Given the volume of carbon dioxide, I'm going to use the volume to get the number of moles. Then, after getting the number of moles, then use those number of moles to get the number of particles. So to get that volume, I'm going to use so we're saying I'm given the volume of carbon dioxide that is produced, and it is produced at what? At STP, like indicated. That's indicated here. So I'm going to calculate the number of moles first. Whenever you're given information, calculate number of moles because every formula is connected to number of moles in chemistry. All right. So now I'm going to calculate this number of moles. Now use those number of moles now here in this formula to calculate the number of particles that are here. Okay? So that's what I'm going to do. So we say the volume is 0.2 divided by a molar volume. Now the molar volume, this is Vm, this is molar volume. You take it from there, it's a constant. You take this one as a molar volume. Okay, so the formula is this, and then Vm is this value here. That is the molar volume that I'm going to use. So the molar volume is 22. That's 22.4. Right, so we got this number of moles. I wrote it in scientific notation because you don't need to round off the answer. Now, from getting this number of moles, I use them here in this equation so that I can get what this one is. So I say N is equals to N over Na, right? Now, the number of moles already I know it is 8.93 times 10 to the power negative 3 is equals to the number of moles. So the number of particles divided by Na is the number of particles. Is Avogadro's number. Is the Avogadro's number, which represents the number of particles in 1 mole, right? So for Na, I'm going to substitute that number there, which is a constant. Okay. So we substituted this, then we get the number of particles as that. 5.38 times 10 to the power 21. That is the number of particles, right? So remember the number of moles that we calculated. The number of moles that we calculated is N is equals to the number of moles of carbon dioxide it was 8.93 times 10 to the power negative 3 mole of carbon dioxide. Right. Now let's look at the question. It says to us, determine the percentage purity of calcium carbonate. All right. So now, to get the percentage purity of calcium carbonate, we now come here to calcium carbonate. Right. We have information about carbon dioxide. And now we want information about calcium carbonate. Right. Now remember, you cannot use this mass here to get number of moles. The impure mass, you can't use it to get number of moles because the impure mass, it is not calcium alone that is inside the impure mass. It is calcium and other things. So if you calculate number of moles, those number of moles won't be the number of moles of calcium carbonate because impure means calcium with other things, other impurities. Okay? So, yeah. Now, what are we going to do? But the calcium that is in the reaction here that we see, it is pure. But the one that is in the statement is not pure, it is impure. The mass that you see here is going to be the impure mass. But when you calculate mass using the reaction, you're going to get a pure mass because it is only the pure calcium that takes part in the reaction. Right? So the aim here is to calculate the pure mass of calcium. So from getting number of moles of carbon dioxide, from number of moles of carbon dioxide that I got, I'm going to use ratio to get the number of moles of calcium carbonate. Then from there I get mass of calcium carbonate. Then after getting the mass of carbonate, that will be the pure mass. This mass is pure. This mass is pure. Right. Now, this mass is pure. Then to get the percentage purity, so percentage purity, I will say the pure mass of calcium carbonate divided by the impure mass of calcium carbonate divided by the impure mass of calcium carbonate times 100. That will be the percentage purity. So let's get into it. Already the number of moles of carbon dioxide, I have them. I already have this number of moles. Now let me get the number of moles of calcium carbonate using ratio. I use mole ratio to do so. Now if I look at this, the ratio between calcium carbonate in the reaction is 1, because the coefficient is 1 here, and the coefficient here is 1 in the carbon. So the ratio of carbon dioxide is to calcium carbonate. The ratio is 1:1. The ratio is 1:1. Now, the number of moles of carbon dioxide, we know it to be 8.93 times 10 to the power -3. Now, which means now the number of moles of calcium will be what? Of calcium carbonate will be what? You just simply cross multiply. Multiply n with that, you multiply this with that. So we just multiply this, we multiply that. So, and again, even if you don't multiply, 1:1 means the number of moles will be the same, because it's 1:1. The ratios are the same. So n is equals to 8.93 times 10 to the power -3 mole of calcium carbonate. Right. Now I got the number of moles of calcium carbonate. Where should I go? Said the next thing is to get the mass. You must get the mass of calcium carbonate. Okay? So in the next page, let me see. So, right, we are going to get the mass. So we said our procedure is as follows. We started with number of moles of carbon dioxide. Then we used the ratio to get the number of moles of calcium carbonate. Then we are going to use this formula here to get the mass of calcium carbonate. Then that mass, we said, is going to be a pure mass, because that calcium is inside a chemical equation. So only a pure mass can undergo chemical equation. Then we take that pure mass, we substitute it here. Then we divide by the impure mass that we were given in the statement. Then times 100. Again, I said use this. We're given the number of moles of carbon dioxide. change those number of moles into the number of moles of calcium carbonate using ratio, right? And the ratio was 1:1. Then use those number of moles to get the mass of calcium carbonate using this formula. Then the pure mass, substitute it here in this formula here to get the percentage purity. So this is percentage purity. Right, so I'm going to say now N is equals to mass over molar mass. Now the molar mass of calcium carbonate, molar mass of calcium carbonate is equals to calcium, the molar mass of calcium plus the molar mass of carbon plus the molar mass of 3 oxygens. The molar mass, if you check in the periodic table, the molar mass of calcium is 40, of carbon is 12, then of oxygen is 16, but that 16 must be multiplied by 3, right? And you'll get a molar mass of 100 grams per mole. So the molar mass of calcium carbonate is 100 grams per mole. Right, the number of moles that we have for calcium carbonate is 8,93 times 10 to the power -3 is equals to mass over mass. And this is the mass that we get. Right, now this is the pure mass. Now I use this pure mass and substitute it into that formula there for percentage yield. So say percentage purity will be equals to the pure mass, which is 0.893. The impure mass was 4 times 100%. 0.893 over 4 times 100. That will be 22.33%. So to explain, right? So for percentage purity, I got number of moles. Use those number of moles of carbon dioxide to get the number of moles of calcium carbonate. Then use those number of moles to get the mass of calcium carbonate, which is pure mass. Then use this formula for percentage purity. Percentage purity is equals to pure mass over impure mass multiplied by 100 because of 100%, right? So the 100 that I got here for molar mass is not the 100 that I'm multiplying there by. No. Right. This one is molar mass. This one is the 100 for 100%. Okay. So